Welcome back to the Deep Dive. You're here to get smart fast, so today we're plunging into something pretty fundamental to modern AI, neural scaling laws.
hmm
Think of this as like your cheat sheet to understanding how bigger models often learn better.
Yeah, that's a good way to put it.
Our mission today, to unpack these laws based on the sources you shared and really see why they're such a big deal in AI development. We'll be looking at, model size, dataset size, and the compute power behind it all. Ready?
Absolutely. So, at their core, neural scaling laws are really about this predictable relationship. It's between how well a neural network performs and the resources we actually pour into it.
Resources like?
We're talking about how much better a model gets as we say, increase its complexity. That's the number of parameters it has, or the sheer amount of data it learns from, or, the computational power used to train it.
Okay. And these aren't just like abstract ideas floating around, right?
Yeah.
They actively shape how AI is built now.
Precisely. They've been, well, really instrumental in the progress we've seen in cutting-edge deep learning,
Hmm?
especially with things like large language models,
Yeah, the LLMs everyone talks about.
right, for text generation and stuff, and also the powerful deep convolutional neural networks in computer vision for image recognition. Scaling laws give us a framework to understand their capabilities.
Okay, so when we talk about performance, these laws focus on two main ingredients: model size and dataset size. Let's break that down. Model size first, that's parameters, right?
Okay.
Weights and biases.
Yep, exactly. Weights and biases.
Why does having more of those, more complexity, lead to better results?
Well, what's fascinating is that a larger number of parameters gives the model essentially a bigger capacity. It can capture more intricate patterns in the data.
Like more connections, more knobs to turn.
Kind of. Think of weights as the strength of connections between the model's neurons and biases as like their activation thresholds. Having more just allows the network to learn and represent more complex relationships from the data it sees.
Got it. And then there's the other side, dataset size, the training data. Seems obvious. More info makes you smarter.
That's the intuition, yeah. We measure it in tokens for language, pixels for images, things like that.
So just feed it more text, more pictures.
Exactly. The more data a model gets exposed to during training, generally the better it becomes at generalizing, making good predictions on new stuff it hasn't seen before.
Right. Generalization is key, not just memorizing.
It's like learning from experience, right? More examples usually lead to a deeper understanding.
Okay, model size, data size. Now the third piece, computational resources. Compute.
Mhm.
This is the muscle. Yeah.
That's it. Compute is what actually lets us train these huge models on these massive data sets without it taking, forever.
And how do we measure that?
So compute is really the engine driving the scaling. It dictates how many calculations we can do per second. The standard metric is FLOPs, that's floating point operations per second, basically raw processing speed.
Higher FLOPs means faster training. Makes sense.
Generally, yeah, more compute power available.
Okay, so we have these three levers: model size, parameters N, dataset size D, and compute C. Often, though, compute is fixed. You only have so much budget or hardware. How do scaling laws help then?
Ah, that's a really practical point. Optimization. If you have a fixed compute budget, these laws can help you figure out the sweet spot, the best trade-off between model size and dataset size for that specific amount of compute.
So, like, is it better to train a slightly smaller model on a way more data or a bigger model on a bit less data, given my limits?
Exactly that kind of question. The scaling relationships can offer guidance there. It helps you allocate your limited compute resources more effectively.
Okay, that clicks. It's not just bigger is always better across the board, but finding the right balance for your constraints. And this is where it gets really interesting for predicting things,
Mhm.
because these laws give us a way to sort of anticipate how good future AI might get just by projecting how these factors, N, D, C, will scale up. That feels like a powerful insight.
It absolutely is. They provide a really valuable framework, not just for understanding current AI progress, but even for making, informed guesses about future capabilities as we keep pushing the scale.
Right. So let's wrap this up. Key takeaway. Neural scaling laws describe these fundamental relationships: how AI performance improves when you scale up model parameters, training data, and compute. It's kind of the blueprint for a lot of modern AI development.
Couldn't have said it better. It really maps out the current trajectory.
And that leaves us, and you listening, with a final thought to chew on.
Yeah, considering this fairly predictable improvement we see with just scaling things up, what happens next? As we keep making models bigger, feeding them more data, using more compute, What are the fundamental limits we might hit? Or maybe even more exciting, what totally unexpected breakthroughs or new kinds of understanding might emerge from this scaling?
Definitely food for thought.
Uh-huh.
What happens when the scaling trends continue? Or maybe when they don't?
Exactly. Something to ponder.